Aviation is not just about airplanes in the sky. It's about the meticulous work that keeps them there. Every flight relies on a network of engineers, technicians, and systems, ensuring millions of parts function perfectly together. From fragile wooden gliders to AI-assisted electric aircraft, maintenance has always been as critical as the aircraft itself. Today, predictive analytics, autonomous inspection drones, and electric propulsion systems are transforming how we ensure safety and efficiency in aviation, ushering in a new era for the industry. Even before powered flight, pioneers like Otto Lilienthal demonstrated the importance of careful inspection and iterative improvement. Every glider he built and flew was meticulously checked afterward. Broken spars, torn fabric, or loose control wires were logged and studied. This early attention to detail established a mindset that remains central to aviation today. Success in flight depends on preparation, precision, and constant improvement. When the Wright brothers achieved powered flight in 1903, maintenance was inseparable from piloting. The Flyer's engine required constant lubrication, the wooden propellers had to be examined for splinters, and the fragile cloth wings needed daily checks. Pilots were also mechanics, repairing and adjusting their aircraft between flights. In this era, maintenance was hands-on, intuitive, and essential for survival. Without it, early aviation could never have progressed. By World War I, maintenance practices became more formalized. Aircraft were no longer rare experimental machines, they were weapons and reconnaissance tools. Fragile biplanes required frequent engine rebuilds, structural inspections, and careful armament checks. Ground crews worked tirelessly to keep aircraft mission-ready. Standard operating procedures began to emerge, laying the groundwork for the checklists, inspection protocols, and documentation systems that dominate aviation today. Even the term "hangar queen" for aircraft demanding constant attention originated in this era. The interwar period brought further transformation. Aircraft structures shifted from wood and fabric to metal. Engines became more powerful, and hydraulic and electrical systems increased in complexity. Airlines formed dedicated maintenance departments, recognizing reliability as a selling point alongside speed and comfort. Detailed maintenance manuals were drafted, spare parts inventories standardized, and technicians became specialists rather than generalists. Routine inspections, lubrication, and scheduled overhauls became common practice, dramatically improving safety and reliability. World War II accelerated maintenance innovation in unprecedented ways. With aircraft fleets growing and missions becoming more dangerous, rapid turnaround became essential. Planes like the Spitfire and B-17 Flying Fortress required entire crews to inspect, repair, and prepare them within hours. Modular engine components allowed mechanics to swap damaged sections quickly, keeping aircraft operational without lengthy overhauls. Wartime necessity also drove documentation and standardization to new heights. Maintenance records were meticulously logged, establishing procedures still fundamental to modern aviation. The post-war jet age introduced new challenges. Jet engines, pressurized cabins, and advanced avionics demanded specialized knowledge. Technicians needed to understand turbines, hydraulics, and electrical systems previously unheard of in piston engine aircraft. Airlines and manufacturers responded with formal training programs and certification processes. Aircraft such as the Boeing 707 and Douglas DC-8 relied on rigorous maintenance to achieve longer, higher, and safer flights. International oversight emerged, with organizations like ICAO defining global standards to ensure safety across borders. General aviation also expanded rapidly. Manufacturers like Cessna, Piper, and Beechcraft made personal and training aircraft widely available. Maintenance for these aircraft remained hands-on, but benefited from emerging standards. The Cessna 172, for example, became a model of simplicity and maintainability. Flight schools trained pilots to perform routine checks themselves, reinforcing a culture of proactive inspection and preventative care that extended beyond commercial and military aviation. The late 20th century brought a digital revolution to maintenance. Sophisticated avionics, autopilot systems, and fly-by-wire controls required new approaches. Traditional inspections were complemented by electronic diagnostics. Engine performance could be measured digitally, hydraulic systems monitored for leaks, and avionics tested for software integrity. Predictive maintenance emerged, using trends in component wear and performance to anticipate issues before they grounded aircraft. Airlines recognized that efficient maintenance reduced delays, improved passenger satisfaction, and lowered operational costs. Maintenance practices evolved alongside material innovations. Composite airframes replaced aluminum on many aircraft, offering performance advantages but presenting inspection challenges. Internal cracks could be hidden from visual inspection, requiring ultrasonic and X-ray testing. Digital logbooks replaced paper records, tracking every repair, inspection, and modification throughout an aircraft's life. Standardized part numbers and serial tracking became essential for global supply chains, ensuring every component could be traced and maintained reliably. Today, aircraft maintenance is entering a revolutionary phase. Artificial intelligence and machine learning are being applied to predictive maintenance at an unprecedented scale. Sensors on engines transmit real-time data on temperature, vibration, and performance to monitoring centers. AI analyzes these streams to predict failures before they occur, optimizing schedules and reducing downtime. Some systems automatically order replacement parts when wear is detected, creating a seamless maintenance ecosystem. Human technicians are shifting from hands-on repair to supervision, problem-solving, and system management. Electric propulsion and urban air mobility are redefining maintenance standards. Electric vertical takeoff and landing aircraft, like those developed by Lilium and Joby Aviation, use distributed electric motors instead of traditional combustion engines. Maintenance focuses on battery health, electrical circuits, and software integrity rather than mechanical overhauls. Data monitoring becomes as important as visual inspection. This paradigm shift moves maintenance from reactive repair to proactive system management. Regulatory frameworks are keeping pace. Aviation authorities worldwide now approve AI-assisted inspection tools, digital logbooks, and condition-based maintenance practices. Standards ensure safety while allowing innovation. The FAA, for example, allows airlines to extend inspection intervals when AI and sensor systems reliably monitor aircraft health. Balancing regulation and innovation keeps the focus on safety while embracing new technology. Looking back, the evolution of maintenance from Lilienthal's gliders to AI-assisted eVTOLs reflects humanity's relentless pursuit of aircraft safety and reliability. The discipline has survived wars, economic crises, and technological upheavals, with each challenge reshaping practices without halting progress. Maintenance has always been the backbone and guardian of aviation. The aircraft of 2026 are safer, more reliable, and technologically advanced than ever before. Yet by 2050, entirely new maintenance philosophies may dominate, emphasizing autonomous diagnostics, electric propulsion, and real-time monitoring. The evolution of aircraft maintenance is a testament to human ingenuity, adaptability, and the relentless pursuit of safer, more efficient flight. If history teaches us anything, it is that aviation never stands still. Safety and innovation have always flown together, and they always will.